Okay, next we're going to discuss decision tree induction. So I'm going to first to give you an overview of what a decision tree is, what are the basic algorithm is. Then we're going to narrow in, zoom in to two aspects in decision tree induction algorithms. So let's first have get a general appreciation what a decision tree is and how does it work. So here I have a sample dataset. It's about whether individual is going to buy a computer or not. So we have a set of attributes, also known as features, on the potential buyers. We have age, income, student, credit, rating. So if we give a decision tree algorithm this dataset, we might get a resulting tree like this. So there are a good number of decision tree algorithms. ID3 was the first one, and C4.5 and the card. C4.1, C4.5 is the algorithm that has been routinely used as a baseline algorithms to compare other algorithms to. Again, decision tree is a fairly robust program algorithm. So let's look at the tree. So what we notice, this tree has one root, and starting from the root, starting from the root node, the node can be split into multiple branches, and a branch can have additional nodes on its path, or it can actually reach one label. This is the final label, the yes no buying computer label here. So what this tree tells us, if this individual's age is less than 30 years old, and if it's not a student, then he's not going to buy a computer. If the age is less than 30 years old, and yes, this individual is a student, then this individual going to buy a computer because our label here is yes. Okay. So the decision tree algorithm just convert this into this, the tree. How internally does decision tree algorithms involve? We're going to use the very basic Hunt's algorithm for decision tree to illustrate the key ideas. Lots of improvements has been applied to decision trees over time, but all the decision trees shares this set of steps. So all the decision tree, vast majority of the decision trees in use are all greedy algorithm. So the decision tree is constructed in a top-down manner. So this means that the tree was started from here, and the nodes was split to the second level. And the second level nodes are split into lower levels, so it's a top-down approach. Greedy means that during this top-down approach, there's no way to go back. You will have to deal with the decisions that you made in an earlier level. There is no go back, recheck, change the decisions or the attributes that you selected, to evaluate at an earlier step. No, you don't do that. The reason you don't do that is it will make the algorithm overly complex. It does not really, in reality, improve the performance. There are algorithms being tried to retreat to a previous decision, but they seem to add to the complexity of the algorithm, not having substantial improvement in general. So it's top-down, it's recursive. What does recursive mean? Recursive basically means divide and conquer. So recursive means that we do similar steps repeatedly, and at every step, our problem becomes smaller. So at this step, this is the root. We have all our training examples here. And then at each step, when we move down, at every node, we decide what attribute we're going to evaluate here. And when we do that, as you can tell, once we have decided this branch, once we have decided that we're going to use age as the evaluation attributes in this node, the training set that meet this criteria and landed in this node is smaller than what we had before, right? So now we're dealing with the same problem. We need to find an attribute to further divide the data, but our problem is smaller because our training examples are cleaner at this node, because at this node, all the individuals are going to have an age of less than 30, okay? So this is recursive. Recursive means that we repeat steps at a smaller scale, at smaller consecutive scales until in the end we solved the entire problem, which is different from iterative. Iterative means we run the same process on every element of every observation of a data set. So divide and conquer, as we have illustrated, that at each step our problem becomes smaller and smaller. So at the start, all the training examples are at the root. Examples are partitioned and split recursively based on the selected attributes. How are we going to select this attribute? We are going to use either heuristic or statistical meanings. There are a set of statistical measures that we use. Information gain is one of those. We're going to actually, this is one, selecting attribute is one of the technical details we're going to pay more attention, and we're going to look at those in detail shortly. So we recursively grow this tree, but then in the end, this recursive process have to stop, right? Because at each step, we have a smaller subset of training examples. Eventually, we're going to reach to the end that we either have no samples, no training examples in a node, or there is no suitable attributes to further divide. All the attributes has been tested through the path that leads to the current node. So the condition for stopping partitioning is one of the following. One, when all samples of a given node belongs to the same class, then there's no need to further split this node. Any sample that landed in this node are going to be applied with this class label. Therefore, we don't need to further split this. The second possibility is there's no suitable attributes we mentioned earlier. All the attributes has been tested. There's no attribute that can be used to further divide the training example in the node. In this case, we're going to assign the most frequent class label of the current of the training set in the current node to label this leaf node. We're going to see some examples shortly. This is pretty straightforward and intuitive. When there's no sample that's been distributed into this node, then we're going to use the most frequent label of its parent node to label whatever observation that landed in this node. So the stopping conditions is one of the three. Either all samples in a given node belong to the same class, or there's no suitable attributes to further divide, or when there's no sample that's distributed to this node. And in each of the conditions that we know how to decide the class label when this decision tree is used. Okay, so let's look at example. My conceptual illustration. So at the beginning, all the classes, we have one training set. And so the color indicates that they belong to the same class. So this is a blue class, this is a green class, we have red class and purple class. We have 5 pieces of data in this data set. So there's multiple attributes. If we at this point decide to use the age to split the data, then based on the age of the observations here, we can divide them into or dispatch those observations into different branches. So observations with age younger than 45 goes to this branch, and in different age ranges they go to separate nodes, child nodes. So we can observe the situation that could happen is we have those two, D2 and D3, they don't have, all the observations that they have belongs to the same class. So there's no need to further divide them. Anybody or any observation that landed in this box will all be labeled as green. Any observation landed in this box will all be labeled as blue. And we have a situation where age greater than 90 does not have any observation landed here. So in this case, we don't know which label to apply to this. Then we're going to use the most frequent label of its parent. This often is just a convenient solution. It doesn't really probably going to result in errors, but that's the default action that we could do. However, when we look at this node, we have two different colors, which means this node need to be further divided. And so the next step what we need to consider is what other attributes that we need to apply here to further divide this the observations here into hopefully two different groups to separate D1 and D5. So this is basically the decision tree algorithm. Splitting scenarios, depending on the type of the attribute, we have a set of different scenarios that can split the observation in one node into multiple sets. So if so I took this illustration from the book. If you have discrete valued attributes, there is two ways that you can partition those. You can either just based on the value, the discrete value of this attribute, create multi-branch partition. So for example, color, we can have red, purple, blue, orange. So every color creates one branch. We could also create a binary branches. So every node always generated two branch. So in this case, we can use set. Whether the color belongs to red or green, if it's yes, goes to this branch. If it's no, go to this branch. Many algorithms took this approach. It makes algorithms easier to write, and in effect, the rules generated are pretty much the same. If you have continuous variables, then you will have you can again have these two possibilities. In this case, we have by testing on those values, we can actually find the midpoint between two observations and find the value to discretize. So in this case, the assuming A is what income. So the income, if income is less than 42,000, goes to this branch. If the income is greater than 42,000, 1000 goes to this branch. It could also happen that you have multiple other choices in between. But again, those binary branches are the most popular ones in terms of the implementation. So in our police shooting data, one of the decision tree that we generated before looks like this. So this is also how you're going to read a decision tree generated by RPart. RPart stands, it's the R algorithm for decision tree. I think it stands for recursive partition. So RPart, a tree generated like this, what you can see here, this is our top node, the root. It covers 100% of the training example. As you can tell, if we go to the lower parts of the tree, the size of the training examples represented in every node is reducing, right? So from 100%, this node we have 16%, goes to this node we have 84% of the observations hosted here, and goes down further we have smaller and smaller number of the observations. So divide and conquer, right? And again, this our part does binary division, so partition here. At first, based on age group, I think we have recognized this earlier in our analysis that age is an important attribute in this data set for the differentiation of the race. So if the age group is either young or grown, then goes to this branch. If the age group is mature or old, goes to this branch. So both branch actually have the most dominant observations being white. So here W indicates the most popular race in this group of samples. So this, the very last, the set of the 6 values here is the percentage of the race in the example hosted in this node. So 39% of the observations in this node is white. So in either case, after this split, what we see here, the most dominant examples are all white. So our labels for those two nodes. So any observations fall into those nodes, they're going to have a white as their labels. So here it's terminal node. So this white, anything landed here is white for sure. But here, since we have additional branches, the observation can actually be further divided. If the age is actually young, go to this branch. If the age is actually grew, then go to this branch. If you follow the young branch, we can see the most dominant observations in this node is actually black. Total number of observations landed in this node is 21% of the regional large whole observation set. Okay. So if we follow again this branch, we can see that if we further divide this group, because it's still very mixed, we have this 0.09, 0.04, and 0.07. So it can still be further split. After further split this time we chose sign of mental illness as a attribute. If it's false, then it's most likely to be black. When we look at this, compare the distribution here to the distributions in this node, we can see this is clear, a little bit cleaner now. We have a large gap between black and other race distributions. So here we have this white, it's almost pure. Well, it's not quite. So if you actually have mental illness, you could have you're more likely to be white than others because white is has twice more observations than other distribution. So when we look at the R-part algorithm in our R exercises, we will realize that we have multiple ways to control how the user has multiple ways to control how we want the algorithm to grow the tree. We can determine how deep the tree is we want the algorithm to grow. The deeper trees will always give you better performance, but they always risk overfitting. We will talk about those issues shortly. So far we have an overview of decision tree. In the next video, I'm going to talk about those two technical details. How do we perform attribute selection, and what's the best way to provide attribute selection, and why we need to prune the tree, and what methods are there for tree pruning. We'll discuss those topics in the next video.